Here we go. All right. Hello, everybody. Hello again. Most of you.
Hello.
You guys are off in the corner.
I know it's the worst angle, man.
Yeah. There are seats in other locations of the classroom that becomes like untenable as a seating location, just so you know.
Thank you.
Worst case scenario, you can just pull out the slideshow on my laptop.
That's true.
Yeah. So. I don't know if I see it.
Oh, by the way, week 3 is currently invisible to us.
Oh, yeah, okay. Thank you. There we go.
Thank you.
I'll give you next week too, why not? There we go.
Treat yourself.
Yeah. You know, because I know like what everybody enjoys doing on the weekend is, you know, pouring themselves a nice glass of wine, sitting down on their favorite chair and reading next week's database slides. So, all right. So today we have, I just did, yeah. Today we have indexes, views, and subqueries to discuss. In terms of sort of lecture content, you can think of this one as a bit of a lighter week, I think, relative to the last couple of weeks, which have been a bit more, you know, gotta get all that basic information into you. So let's start. Indexes. So this is what we will be discussing regarding indexes. So a lot of this course kind of boils down to talking about different numbers which have different purposes, right? We've talked about keys, key values, right? Primary keys, foreign keys. And does somebody remind me what the purpose of one of those is?
The primary key is it's an identifier for an item that is not repeated and is specific to that item.
Right. A unique identifier for each record in your in a table. Right? Very good. How about a foreign key? Does anybody remember what a foreign key is?
A key that makes reference to primary key of another item.
That's right.
So
So-
another table.
Yes. So when we have a table that has a column of keys, but they're not the keys for these rows, they're the keys for other rows and other tables, that is a foreign key. Indexes seem like they would be related to keys, but they're actually not. They solve a different problem. It's more of an internal algorithmic problem. So, when you have a select statement, which is just give me everything in the table, this can execute very quickly. You can imagine, however, the more things you require from your select query, the longer it takes to process. In particular, ordering takes time, right? Where is a filtering operation? You must perform the filtering operation for each record in the table. So you are talking about an algorithm that its runtime is proportional to the size of the table and measured in number of records, right? This is kind of like an algorithm-y kind of way of thinking, right? So if our, if our table is 500 entries, that's not very large, takes 500 operations to get there. If it's 5 million, that's certainly much more than 500, but, 5 million is still a fairly low number of things for a computer to do, right? Can execute it reasonably quickly. Sorting is a bit of a different beast. Sorting requires look back. If you implement a basic sorting algorithm, insertion sort, bubble sort, something of that nature, your sort of brute force sorting algorithm will be proportional to the square of the number of things in the table, the number of records in the table in this case. So, for example, if we have 500 squared, right? Anybody tell me what that is? Yeah, it's 250,000, right? How about this one? Right? Well, we got 25, followed by how many zeros? 12. So, 1,000, million, billion, trillion, 25 trillion, right? As large numbers go, that's a pretty large number. You can imagine this is now to a size where it takes time, right? This will take time. Sometimes, if you're trying to sort a data set that's large enough, it takes quite a lot of time indeed. Hours to days even. So, given that sorting data is something that we have to do quite a lot of, right? We want to have something in there which allows us to sort it more quickly, right? By the way, this is even worse if it's strings that you're supposed to be sorting, because strings, in order to determine whether one string is greater than another, according to dictionary ordering, you have to go through each letter comparing, right? So, oof, basically. It's basically a big oof.
It'll take a hot minute.
It will take quite a few hot minutes. So, the idea of an index is that we are attempting to speed up ordering operations by keeping a kind of secondary column, normally a hidden column, where the order of things in the database has been pre-calculated, right? That way, we don't have to resort the data every time we need to pull data from it. We just look in our column of indexes that tell us when where things are, and boom. Right? Does that make sense? That's kind of the idea. So, let me just go through the slides a little bit more though. So, yes. So, another key thing about whether or not you get better performance out of a database by using indexing and these types of techniques, when you create an index, and incidentally, like a not bad mental model is, oh my goodness, I was about to say something that dates me. I'm going to say it anyway. Back in the old days, and you might still see this in little community libraries way out in the country, right? Book catalogs used to be on index cards. right? The purpose of the index card was to be able to thumb through the books to see what was in the library quickly, right? And you would order them according to, various ordering systems. The most famous ordering system is the Dewey Decimal System. Don't ask me how it works, but it exists. And so this is kind of the same idea. Rather than writing our data onto cards, we're simply taking like the card number and making that into its own column. Does that make sense? So, but the problem is the frequency with which you access the data and the frequency with which you put new data in affects whether or not this is a good idea, right? So if your database is the kind of like, it's kind of almost containing fossilized data, right? It's like, data that does not change frequently. For example, this is probably not as true as you might think, but let's imagine like the government has a database of tax records, right? Something, whenever you file your taxes, information from your tax return is put into a database in the government. You can imagine that's the sort of thing they would do, right? How often do you do your taxes? Typically. Once a year. So the number of times that you're inputting data into the table is infrequent. Now, the government pulls that data for all kinds of purposes, right? Determining your eligibility for things like the Trillium benefit, for example. They pull your tax return information to determine your eligibility, right? You can imagine that that is done like, maybe not like per program on a frequent basis, but if you count up all of the different government programs that access your tax information over the year, right? Maybe you're working with a ratio of like, that data gets written once for every 20 times it's read, that data gets written once for every 100 times it's read, right? Something like that. So the higher that ratio is, the more effective these types of time-saving devices are. Because when you enter new data, it must be re-indexed with existing data, right? It's like, okay, some code now, or not code, some data, let's do data. Let's say that you have some strings. Oh, this is a terrible marker. Blech. Try this time. Oh, that's even worse. Is this a dead marker too? That one's better. This is an acceptable level of marker. So let's say we have A, C, F, E as strings, and we are creating an index for them, right? Let's say that we are indexing these according to ascending order, right? What's the first one alphabetically? Good. What's the second one?
C.
What's the third one? What's the fourth one? Very good. So far, everybody passes elementary school. So, here's the issue though. What if a new database record is made inserting V?
Oh, it's gotta recalculate everything.
It's got to recalculate everything. That's right. A is fine, but this is no longer 2, that's no longer 4, this is no longer 3, right? B is now 2, C is 3, E is 4, and F is 5. I don't know why I decided to put these in different columns, that's just silly. Silly, silly, silly. Right? So, in order to maintain the sortedness of this column, anytime you insert information into it, these indexes need to be recalculated. Which makes sense, right? Because if, like, when you get new data in, it's normally not going to be at the beginning or the end of your data set alphabetically, right? You're going to have to calculate where it's going to be inserted into the order. There you go. Now, it turns out that that's not as bad an operation as sorting in general, right? So, to take random data and sort it, again, you guys haven't yet seen big O notation, but some of you may have heard of it. How many people have heard of big O notation? Right. So the general idea behind big O notation is this is the complexity of the algorithm. This is how fast the runtime grows proportional to the number of things it's processing. In the case of databases, N is number of rows, number of records. So to just sort the data, assuming you're using like just a very simple sorting algorithm, there are better sorting algorithms than this, that's proportional to the square of the number of rows you have. If you're using a good sorting algorithm, the best you can do is something like this. N times the base 2 logarithm of N. Better, but still not as good as this, right? So a linear, these are called linear algorithms. Big O-N is a linear algorithm. What that means in terms of code is that you can do something by making one pass through the data, right? Now, if you already have something that's sorted, inserting one more thing into it in such a way that it preserves sortedness is a linear operation. You simply walk through the thing until you find the position where, the next item is greater than the thing you're trying to insert rather than less than, right? Then you say, okay, I insert it here, and I move every index down by 1 past that point. Linear operation, right? So you're still saving time versus having to do this every time, right? But again, it has to do with the frequency with which you're adding or removing data. This is also something that you have to worry about with removing data, right? The frequency of modifying the table versus reading the table. How often are select queries run versus insert or delete queries? Does this make sense? So far, so good? All right. Good. So, an index is a separate structure pointing to the table data. Multiple indices are allowed on one table, so you can index multiple things in the table. The things you index, and you choose what to index when you set the table up. The things you choose to index should be the things that you order by, right? Or at least the things you order by frequently, particularly if they're strings. Indices consist of one or more columns. Use is transparent once created. So once you have configured the database to have an index for a particular field in the database to be indexed, you don't have to do that manually. the database system knows what an index is and knows how to use it. All you have to do is set it up in the first place. It's kind of like how you don't actually need to know what the sorting or searching algorithm the database is using is, right? So, the advantage of using an index, it reduces access time. The whole point. Disadvantages, requires storage space. So we are trading memory for time efficiency. As you go through your careers as budding computer scientists, you will find that that is a trade-off that you get to make quite a lot, actually. You can trade some memory and get back time. In the olden golden days, you had to be careful about how many times you did this, because memory was a scarce resource, right? The sorts of computers that I had when I was growing up in the 90s, not that I'm dating myself or anything, I was born in 1988. My first computer was my first computer that I really had was a compact Presario, which was a 486. Some of the older people in the class may remember them. It was originally Windows 3.1 that was eventually and mistakenly upgraded to Windows 95. Before that, my father had a Linden Series Pro, which is one of those old ones that didn't even have color. But anyway, back in those days, that poor old compact Presario, it had RAM that was measured, I think it had something like 16 kilobytes of RAM, right? That's it. How much RAM do your computers have now, right?
64 gig.
64 gig, right? So the memory time trade-off, like processing speeds have increased, certainly, but memory density has increased way faster than processing speed has increased. So these days, you take that bargain. Every time it occurs, you spend memory and you get runtime. That's what you do now, because memory is so damn cheap. Back in the old days, not so much, but these days, you always make that bargain. Caching is another topic you might look into. So this is generally worth the storage space. Now, it also kind of depends on whether you own the server and the storage space. If you're being charged money for the amount of gigabytes of storage that you're using, then you're back into a situation where maybe that's like a financial consideration in terms of optimization, right? But certainly on your own hardware, memory is pretty cheap these days. Memory is pretty cheap, I'm sure, like using the cloud services and that sort of thing as well, but you always got to be careful when you're paying for it. So, indexes need occasional rebuilding. See example. Slows down insert and delete and possibly update processing. I would say definitely update. If you update this to be Z, right? Z, this is no longer correct. So you need to rebuild it. Right? Make sense? So why is sortedness such an important property? I read in a textbook once, and this is probably even more true than it used to be, given that we now live in the age of the database, and we live in the age of big data, right? I read in a textbook once that 1/3 of all computation power is used sorting things, right? Why? There are lots and lots of algorithms that you can use on sorted data that you can't use on or unsorted data. And some of these algorithms are really, really good, right? So take, for example, the binary search algorithm. Have you folks heard of the binary search? How many people have heard of it? How many people could explain it if they had to?
I
Yeah.
can explain it if it's the thing that I'm thinking about.
Okay, well, I will confirm if it is the thing you're thinking about, and then, yeah, I won't require you to explain it. Yeah.
Oh,
Yeah?
I can
Oh, you have a
try.
question?
No, I can try. Like it's like sort divide in the middle and and again divide in the middle and search within the first half and then second half like this.
Mm-hmm, exactly, and then recursively continue that. So, all right. We're gonna do binary search right here, right now. And don't worry, I'm sure we will still finish our class today. So, I'm going to pick a number, 5. Someone give me another number that's greater than 5. 6. 27.
7.
7 is not greater than 27.
Oh, I see, you
31.
did it in the last one?
Yes.
Alright, 29.
29. 30.
86.
86.
92.
92. 100.
100,000.
100,000. 200,000.
That went from 0 to 10 really quickly.
Yes. So to speak. That'll probably be enough. So let's imagine we are trying to determine whether the number 42 exists in this data set. Our target number is 42. So, because this will be stored in an array or using indexes, we also know what index at which each of these is stored. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. So now, the binary search algorithm operates by picking the number in the middle. If there are 2 numbers in the middle, you pick one of the numbers in the middle, right? So, what's one of the numbers in the middle? 86. We examine 86 and compare it to the number that we have that we're seeking, right? We'll do it a couple times. Is 42 greater than 86? No. So because the data is sorted, and only because the data is sorted, we know that it must exist in this half of the data. Right? So we have, so the way to think about binary search is to think about the concept of a search space and narrowing of a search space. The thing I'm looking for is in this region. If I can eliminate a chunk of values where it's not in that half, the remaining half is where it must be, so I've reduced the search space by a factor of 2, right? So, I know that it must be in this half. I then repeat the same step again, and this is called recursion. We recurse on the front half of the data set. So what's the number in the middle of the front half? 27. 27. Is 42 greater than or less than 27? It is greater. Therefore, what half can we exclude? We can exclude this half the same way we excluded that half. So we know that the value must be here. In this particular instance, there's kind of an implicit step where, like, if the middle value happens to actually be the value you're looking for, you win the jackpot, and you can just stop. Alright? So you pick the middle-ish value of 2930, right? So let's just say we pick 29, right? Is 42 greater than 29?
Yeah.
Yes, it is. So if it exists, it must be here. That's 30. We only have one element left. Is that 42? No. So, false. The data we're looking for is not in the array. That's the binary search. Let's do it for something that's in the array, just for, just for the sake of interest. Because this is the interesting part of the lesson. Let's say that we are looking for, somebody give me a number in the array.
100,000.
100,000. All right. Is 100,000 greater than 86?
I think so.
Last time I checked, right? So somewhere in here. Middle value,
Yes.
let's say 100. I don't know why I'm like leaning to the left today. 100 is our middle value. Is 100,000 greater than 100? Certainly it is. So here we go. Middle-ish value here. Is that equal to the number we're looking for?
Yeah.
Yes, it is. So true. And normally these algorithms don't just return true, but the index at which the true value is. So
I feel like the likelihood it is to return true just increases as the database gets smaller.
that is precisely the case, yes. So this is a classic example of what's called a divide and conquer algorithm. So the search time for this is big O base 2 logarithm of n. This significantly outperforms linear time. The only thing better than this is to take no time at all, which is to say constant algorithm, constant time algorithm. That literally it doesn't matter how much data you're crunching, it always takes the same amount of time. Like hash tables. Hash tables are magic. So, no. Sure. Base 2 logarithm calculator. Oh man, there we go. So if we wanted to process 100 items this way, we require 7 steps to do so through this algorithm. 1,000, 10 steps. 10,000, 14 steps. 1,000,000, 20 steps. 1,000,000,000, 30 steps. 1,000,000,000,000, 40 steps. You see? This is an algorithm of power. So, that is why you sort your data. Because you can crunch through stupidly large amounts of data in a very short amount of time. QED. QED is Latin for quod erat demonstratum, which is a thing that you say after you prove things mathematically. This did not rise to the level of mathematical proof, but nevertheless it's fun to say, so I said it. I'm at a college and not a university, so I can say that.
So I have a question.
Yeah.
For the index, we need binary search.
So you don't have to implement it. Those are the types of techniques that the database system will use automatically. All you have to do is set up the indexing. Yeah. Nevertheless, binary search is fun and I like teaching it.
Yeah, I just did the math on that. As an example, if you were to try and find a random individual second within the entire history of our universe so far, it would only take 59 steps using binary sort to find it.
I love it. Yes, logarithms. Have fun in data structures and algorithms. Yeah, you guys you take it in 4th semester. And if you really enjoy the stuff in data structures, the Math of Gaming class, which is like an upper year option for those of you in the 3-year program, that you should think of as Data Structures Part 2. So, yeah. Good. So index clustering. Index clustering physically sorts the data according to the clustered index. Only one clustered index is allowed per table. Frequently, the primary key is clustered because, of course, when you're looking for things, you're often looking for them by the primary key. However, based on usage patterns, it may make sense to cluster a different index. Now, why would we need an index for the primary key? I thought the primary key was already a sequence of numbers.
Because that is easy.
Yes, well, it depends on what type of key, right? So remember, there are 2 different approaches that you can take to your keys. One is the M-bun. You guys remember M-buns? Meaningless but unique numbers, right? And the other one is, I forget the acronym, but it's like crypto keys, basically, right? Cryptographically random number sequences, right? So if you're using sequentially numbered keys, then it's already an index, right? You can't actually just, you can search on it directly. It's already in order, right? But if that is the cryptographic, random series of characters, those things are not even close to being in any kind of order. In that case, it does make a lot of sense to have an index for your primary key. Does that make sense? Good. The goal of the class is that things make sense. So, here we go. For example, here is a patient's table. Here is a primary key index clustered, which kind of makes the point I was trying to make. Do you really need this? 1 gets 1, 2 gets 2, 3 gets 3, right? I would argue that this is unnecessary unless your patient IDs are something other than the exact thing you would be adding to the table, right? However, going by last name, that's a bit more useful. You can see that the ordering here is not, the ordering here is not corresponding to alphabetization, right? If we flip back, you might pick up the pattern. So pick a row in this table and watch for where it goes. Right? So basically, we have our position in the table recorded in the index, and these are alphabetized otherwise. Does that make sense? Cool. All right. So, creating an index then. Create is the keyword you use. Index, index name. Optionally unique or clustered. On table name. You then have to specify what field or attribute you are assigning this index to, and whether it should be ascending or descending.
What does it mean by cluster?
So the clustered index, here we go. It physically sorts the data according to the clustered index. So if we are clustering, for example, in this case, last name, right? If last name has been clustered, then the last name row has been physically sorted according to that cluster, that clustering, right? So if I select last name to be the clustered item, the rows are actually moved to do this. However, you still need to know like what the original order was, so that's what the purpose of the second column is. Does that make sense? Come on. So, you need to create a name for the index as well. There's, of course, standard naming conventions for doing so. Please don't choose a name like X or Y. Choose something meaningful. Even though the index is not something that you should ever have to interact with directly, it should just speed things up in the background without you having to really do anything. It's still, you should still name things correctly and usefully in case anything goes wrong and you need to read anything, right? So, it's just good practice. So, and here's a slide on primary key in case you forgot what that is. Everybody knows, we actually started the class with reviewing what primary key was, so moving on. So, views. What is a view? View is our second of 3 topics today. So, a view is a virtual table which is composed of one or more other tables. A view is a result set not permanently stored in the database, but regenerated each time you request the view. Essentially what a view is a stored select query. You store a select query, you give it a name as a particular view, and then when you ask for a particular view, it runs that query. presents you with the table. Does that make sense? So it's like, if you want to take the output of a select query and treat it as if it were a table in the database, even though it's not a table, right? It's calculated from tables at the time it's used. It is a table, like in the sense that the data is tabular, but it's not stored. Yes?
So in Excel, you can like enter something to search for in the table and do find all, and it will give you a list of everything that contains what you typed. Is that kind of like a view?
Like it'll pop up like another little like sub view that
Yeah,
contains all
you can
only
click
that.
on, you can click on one of them to immediately jump to it, yeah.
After a fashion. So let's keep going and we'll see an example.
Okay.
Question, sorry?
So is view stored?
The data contained in the view is not stored.
Okay, so it's just executing a query.
It's executing a query, but it's presenting the results of that query as if it were another table. So for the purposes of other queries, you can select something from a view, for example. Does that make sense? We'll see. So, views are available in the information schema at views and at tables. So this is like part of the point of the view is it is not the primary data, right? The view is not stored in hard memory, long-term storage. It is not on the hard disk. It is like, okay. So to explain the difference, it kind of like, the difference between RAM and ROM is basically the same. So you guys, who can tell me what ROM stands for?
Read-only memory.
Who can tell me what RAM stands for?
Random
Random
access
access
memory.
Very good. What's the difference?
One stores, one does not.
ROM can't be changed.
Well,
Well, not like,
So if you lose power, the RAM, everything on it is lost. But if like you lost electrical power, if it was stored in the ROM, it would still be there if it wasn't power.
yes,
it's not like always actively changing.
yes. It is a lot more expensive to write to the ROM. It takes longer, it takes more electrical energy usually.
I also remember the old CD burners to burn CD-ROMs.
Yes, CD-ROM, yes. Read-only memory, right? So, you know, back in the old days, have you ever like watched an old James Bond movie and seen like the computers that they had in the 70s with like the big spinning disc things on the front, right? And they're like that. It's actually like operating on the same principle as a cassette tape or a VHS tape. You've got a magnetic strip that feeds through a machine, and the cells in the magnetic strip can either be flipped to a 1 or a 0 based on the polarization of the magnet. This is how data used to be stored, which is why it used to be a big thing to not get a magnet around a computer, right? Because you would literally reset all of the data because it was, you know, exposed to a strong enough magnetic field, all your data was spiked, right? We then basically took that and put it inside of a shielded case on little magnetic disks, right? Floppy disks were an early version of this where it was still, you know, they were floppy disks because you could flop them around. But, you know, when you stored magnetic data on a disk like that, you know, you had to have a little magnetic read head that went to a position on the disk to write it in, right? In contrast to random access memory, where you have little pieces of electronic circuitry, which are holding 1 or 0 states, which if they lose power, they lose whatever they were holding, right? The analogy here, your tables are like your ROM, right? That is the permanent data. The view only ever exists in RAM, right? It is like a variable in a programming language that you've used, like the variables in programming languages that you've used before. It's not permanently stored. It is created when needed and discarded when it's no longer needed. But it presents the interface of a table, right? It's a little bit like array lists in Java, which, although they are arrays under the surface, they present the interface of a list. So views present the interface of a table, but they are not tables, they are not stored permanently, they do not contain permanent data. All the data they contain is derived from the permanent data. Does that make sense?
Just a way to show the information, basically.
Yeah, well, there are a couple of reasons that you would do such a thing, right? So, you can limit access to tables using these, right? So, you can set user permissions for a database on a per table basis. You can also set it on a per view basis, right? So let's imagine, just for the sake of interest, we have our patient's table having 14 columns. All of this information is in there. Anybody who has full permission to the table, to access the table, can get, quite a lot of information, perhaps more information than they need to do their job, right? Let's imagine that we have for example, someone working in the ICU, right? When they are looking at people who have been admitted, perhaps the only thing that's relevant to them is the patient ID, the admission date, and the discharge date, and only for people who actually are in the ICU. That's another one, right? So it restricts and filters the data to only the data that the person needs to do their job. In this way, it is enacting something called the principle of least privilege, which is a very important concept in data security, right? So the principle of least privilege is that a person should be given no more access to the system than is required to perform their job, right? It doesn't make sense, for example, for a nurse to be able to access personnel records, right? This is not something that this person should have access to. Now, when you're setting a system up, you can set it up in such a way that most people have access to most things. But this only really works for small systems where you know personally all of the people who work for you. In a large organization like a hospital, you should absolutely assume that people will, look up stuff that they shouldn't, basically, right? Like, if you give people an opportunity to look up information on other people, they will do so in order to exercise things like petty grudges, because people are awful. So just give people only that which they need to do their jobs, and you lock them out of everything else, give them permission to do stuff in an extended fashion should it be required and only with examination, right? This is actually a very good principle for programs and operating systems and that sort of thing as well. You should not, for example, give a JavaScript script direct access to your file system, right? Because, well, first of all, never trust the client, but second of all, JavaScript is, wonderfully arbitrary code that has been downloaded from anyone on the internet. If JavaScript had access to your file system, it could very easily put something in there that you don't want, viruses, etc. This is how back in the day, you would have all kinds of malicious programs installed on, your typical Windows 98 machine and that kind of stuff. The joke of like, the person's computer is just like ad pop-ups for all kinds of stuff, and like they don't even have a browser open. It's just they turn on the computer and it's like ads. That's because people managed to install programs on their computer that did that, right? And that's one of the mechanisms you would have to do that. So if you restrict things, only give things as much access as they require, and be sparing about that, it's a good principle of general security. Does that make sense? Very good. Yes. So, but one of the things that views provide you, because it appears as a table, you can perform queries on the outputs of this query, right? So perhaps it's useful for the ICU nurses to have this table of everybody in the ICU, but perhaps that also at some point needs to be searched for something. You don't want to have to pre-bake every possible query that a person might make in the ICU, right? First of all, you can't physically, right? And even if you could, you wouldn't want to, right? So give them the table and let them search the table, right? Is this making sense? Any questions? All right, let's go back a bit. So these are other create queries. Create view, give it a name, as, and then you select. You can apply some select query, you can apply all of your select stuff from there, right? So you'll notice the first line, create view ICU as. If we remove that, we have just a regular select query. Syntactically, from this point forward, it's just normal select land, right? All we've done is we've put this guy at the front, and basically, it's a little bit like binding it to a variable. That's one way of thinking about it, You're binding it to a name. Make sense? Okay. To use a view, you simply use the name of the view where you would use the name of a table. They function as tables. Now, what's going on under the hood, when you select star from ICU, again, the ICU table is not pre-baked. The database will look up that select query, execute it, return the results, and then plug it into this select query.
Select from the select query.
Precisely. You're selecting from select queries. You can actually, you can do this an arbitrary number of times. Ezra? Like if you want to, you could make a view of a view of a view of a view if you wanted to. So, any questions? Subqueries then? Our last topic for today. So, this is going to be a very long-winded explanation of the fact that you can use braces. You can use braces. You can put braces into a query, and inside the braces you can put another query. This is called a subquery because it is a query within a query.
So in that way, is it kind of like selecting from a view almost, similar?
Yeah, it's like doing it in place without binding it to a name.
Yeah.
Although it depends on the type of query, right? Views must be select queries. I'm not convinced that subqueries are required to be select queries. It probably is a more general mechanism than that. It's almost like the difference between binding it to a variable or using a lambda and using it anonymously. So, sometimes it is necessary to use data from one table to access data in another table. The so-called query within a query. So subqueries, okay, so here's a good difference between the two. Subqueries must only return one column, whereas with a view, they may return multiple columns. A subquery may return multiple rows, depending on how it's used, and subqueries can be nested, so you can have queries within queries within queries within queries. So let's take a look at this one. Select star from medications, where the medication cost is greater than, select average medication cost multiplied by 2 from medications. Order by medication cost, descending. That actually even reads pretty well as English,
Yeah.
That's one of the nice things about SQL is it reads, you can kind of read it. But what this is doing, right? What the subquery is calculating is the average medication cost within the medications table, right? Multiplying it by 2, so we have twice the average. We then pull out, in the outer query, each medication with a medication cost greater than that, and then we order them descending. Make sense? So, in terms of order of execution, as with any other programming language, the inner thing is calculated first before the outer thing. The thing that requires the information waits until the information has been calculated and then uses that information. So, for example, our inner query would result in the following data. You'll notice no column name has been assigned to it. That doesn't mean you can't read it. So, this number might be the number. Who knows? Depends on the data. The main query is then processed using the subquery result set. In the case where it returns just a single number, this is perhaps the most obvious case, because we are talking about just a simple and straight numeric substitution. We simply take the result of the subquery, substitute it into our outer query, and we're off to the races. Make sense? A lot of the time, you're going to be using these in combination with your aggregate functions, things like average, count, max, min, sum. All of these functions result in a single result anyway, so they already meet the condition that the subquery must return only a single column, right? And because they return a single value, we can substitute them directly into Boolean expressions like the one in the previous slide. Make sense? So, in this particular case though, if our subquery were to return more than one row, the previous query would fail. This guy here. Let's imagine that, for no reason in particular, the output of this query were something like 8, 4, 13. Right? At that point, the greater than operator becomes a nonsense. Right? How can one value be greater than or less than a table? Right? It's nonsense. So you have to change the type of operator that you're using in this clause to match the sort of data that the select query is giving you. So, for example, can I make that a little bit bigger? You poor people in the back. Hate everything. Hate it. Hatred, simmering, boiling hatred.
Oh my god.
There we go.
So many clothes.
I need it for later, unfortunately. So, let's consider the following. Our inner query is select nursing unit ID from nursing units where beds is less than 10. Right? So the nursing units table is basically a table giving departments within the hospital, right? ICU would be one of them, right? This is giving us the ID number of every unit that has fewer than 10 beds. Sure, okay. That means that what that is a table of IDs, right? A table of keys. We stick that into a where clause, where nursing unit ID is in this table. That is a different sort of query. Remember that the in query is testing to see if a value is contained in an array or a table or, an aggregate data structure, right? This is an operation which is performed over multiple pieces of data. Since we have multiple pieces of data, that is appropriate. What this is ultimately doing, select these fields from admissions, so we're looking for all patients, this information about all of the admitted patients, where they are in units where the number of beds is less than 10, and then ordering them. Right? Now that's a fairly complicated query. That's a fairly complicated thought to express. But that is the power of a subquery. Make sense? Any questions? So, here's an example of what that might result from, or what might result from the subquery. Nursing unit ID might be CCU, ER, ICU, and OR. We then match, basically that gets substituted in as an array, right? In the same way that a single value was substituted in as a single value, multiple values get substituted in as an array. We satisfy the syntactic requirements of the in operator, and so we go. So, here is an example of a nested subquery. So we're getting queries within queries within queries now. Which one is the first one that would be processed?
The innermost one.
The innermost one, which color, the color is?
Blue.
Blue, yes. So in this case, we are selecting the average quantity on hand from items, where the item ID from items, where the quantity on hand is greater than the average quantity on hand from items. We then select the purchase order based on those item IDs. So this gives you the purchase orders for all items where the quantity on hand is greater than the average quantity on hand for all items, if you were to express that as an English sentence. So, again, we are expressing more and more complex thoughts, right? The sentence we needed to describe what that's pulling from the database is now, like, quite complicated versus where it was before. But still useful. Questions? In summary, index, views, and subqueries.
Oh, I gotta write that one down.
Now hold on, we still have 7 minutes left in class, good grief. Let's see here. Did I release the assignment? I did? Okay, let's take a quick look at it.
Is this in class or out of class?
We're gonna do this in class
Okay.
tomorrow.
Oh, got my slides on the plate.
Yeah, okay, let's get out of here.